When a force is applied parallel to a displacement, work is done. Sometimes we are interested in the rate at which work is being done. This concept, the rate at which work is done, is called power. When a force F is applied to an object in the direction of displacement d, the work done on the object is equal to the magnitude of the force F times the magnitude of the displacement d. The average power, P bar, is equal to work divided by the elapsed time. If the power is constant in time, the instantaneous power P is equal to the average power. The work done is equal to the power times the time. The instantaneous power is the time derivative of the work. The unit of power is the watt, which is equal to 1 joule per second. The block is moving at a constant velocity and constant power is being applied to it. We know that the power is the work divided by the time. The definition of work is the scalar product of the force and the displacement. The displacement divided by the time equals the velocity. Therefore, the power is the scalar product of the force times the velocity. In the case of the projectile shown, which of the four statements below about the power applied by gravity is true?
Correct.
What is the power being applied to this block by the donkey if it is being pulled at a velocity v and the coefficient of friction is mu? The forces on the block along the displacement are the force of friction and the force F. Because the velocity is constant, these forces must be equal. The magnitude of the force F is therefore equal to the magnitude of the friction force, which is equal to the mass of the block times the coefficient of friction mu times g. F is parallel to the velocity, and thus power is the magnitude of the force times the magnitude of the velocity. These equations can be combined to obtain the power.
When someone throws their tennis racket in the air after winning a match, its motion, at first glance, seems rather complex. But if you look carefully, you can see that the principles we've been studying on motion apply here too. A single point appears to represent the movement of the entire mass of the tennis racket as a whole. It follows the same trajectory as a tennis ball hit into the air. This point, known as the center of mass, acts as if the entire mass of the object is concentrated at it. Every object has a center of mass. One way to find the center of mass of a small object is to use a plumb line. Hang your object from any point on the object and attach the plumb line to that point. A plumb line consists of string with an attached heavy weight, and it hangs perpendicular to the Earth's surface. A line drawn along the plumb line will pass through the center of mass of the object. Repeat the procedure choosing a different attachment point and draw a line along the second plumb line. The center of mass of the object lies at the intersection of the plumb lines. If an object is symmetrical and uniform in density, it's easy to guess its center of mass. For example, where do you think the center of mass of this meter stick is? That's correct. It's at the 50 centimeter mark. The center of mass of all these objects is located at their geometric center. Where is the center of mass of this flat map of the contiguous 48 states? If you need to convince yourself of this, you can print the map on heavy stock and use the plumb line method. It is not always possible to use the plumb line method. We need an analytical method for determining the center of mass. Let's start with a system consisting of two discrete particles along an axis. The center of mass of the system in one dimension can then be defined in terms of the masses of the particles and their positions along the x-axis.
These calculations can be applied to real-world problems. Let's look at the SunEarth System. The Sun is considerably heavier than Earth. Current estimates are that the mass of the Sun is about 1.99 times 10 to the 30 kilograms, and the mass of Earth about 5.98 times 10 to the 24 kilograms. The Sun also has a much larger radius than the Earth, about 696,000 kilometers, or a little more than 100 times the average Earth's radius. The distance from the center of the Sun to the center of Earth is, on average, about 1.5 times 10 to the 8 kilometers. Assuming the mass of each body is concentrated at its center, where is the location of the center of mass of the Sun-Earth system? Let's work through the solution together. First, calculate the location of the center of mass of the Sun-Earth system. It is found by using the center of mass equation, where x1 and x2 are the coordinates of the Sun and Earth respectively. Of course, x2 minus x1 must be equal to the Sun-Earth's distance, d. To simplify the computation, let's define our coordinate system such as its origin coincides with the center of the Sun. Then x1 is equal to 0 and x2 is equal to d. The location of the center of mass is then given by the simple relation xcm equals m2 times d over m1 plus m2. Since the mass of the Sun is about 33,000 times the mass of the Earth, then the total mass, m1 plus m2, is approximately equal to the mass of the Sun, m1. Therefore, we obtain the location of the center of mass as a function of the mass ratio m2 over m1 and the distance d. Let's now replace m1, m2, and d by their values. We find that the center of mass is located at 450 kilometers from the center of the Sun. This distance is much smaller than the Sun's radius. The center of mass of the Sun-Earth system is thus located well inside the Sun. Now let's try to determine the location of the center of mass of other systems. When determining the center of mass in 2 dimensions, the equation for the y-coordinate is similar to that for the x-coordinate. We can also use an abbreviated notation to write equations for systems with more than 2 particles. The subscript I represents any of the particles, and the sum runs over all the particles of the system. If we were to calculate the center of mass for a 3-dimensional system, we only need to add another equation for the z-coordinate that is similar to that used for the x and y coordinates. Let's consider an example of a 2-dimensional system where the masses of 3 different balls are assumed to be concentrated at their centers. The xy coordinates of the ball's centers are indicated on the diagram. What are the xy coordinates of the center of mass of this system? Place the mass and coordinates of each object by their values. Now, how can we determine the center of mass of an extended object? Take a boomerang, for example. We can think of it as composed of 3 pieces. We can then determine the center of mass of the boomerang using the location of the centers of mass of the individual pieces and the mass of each piece. What are the coordinates of the center of mass of the boomerang in our example? Correct. To determine the center of mass of the boomerang, write the x and y coordinates of the center of mass for 3 different objects. Then replace the mass and coordinates of each object by the mass of each individual piece and their center of mass coordinates. Note that in this case, the center of mass of the object lies outside of the object. It's relatively easy to calculate the center of mass in multi-particle systems, but in real life, we are mostly concerned with rigid bodies. However, we can think of a rigid body as a collection of tiny particles, each of mass dm. Thus, the summations in our previous equations become integrals in our equations describing the coordinates of the center of mass for a rigid body. Now let's look at an example of a uniform rod of length, L. First of all, let's define the x-axis as being along the rod and the origin of the system at one end of the rod. Then we need to determine the relationship between a tiny amount of mass dm of the object and its position, x. A simple way to do this is to use the linear density of the rod, lambda, which is equal to the mass, m, of the rod over its length, L. Therefore, our tiny mass dm is equivalent to the linear density, lambda, times a tiny increment of length, dx. We can determine the x-coordinate for the center of mass of the rod using the equation for the center of mass of a rigid body. Substituting lambda times dx for dm, we obtain x center of mass is equal to 1 over m integral from 0 to L of lambda times x times dx. Since the rod is uniform, we can put lambda in front of the integral and integrate x dx from 0 to L. If we recall that the integral of x dx equals 1/2 of x squared, we obtain x cm equals lambda times L squared over 2m. Substituting m over L for lambda, we find that the location of the center of mass, xcm, is L over 2. We can easily see from the geometry and symmetry of the rod that this is indeed the correct answer.